Welcome back, students. In this video, we'll continue our discussion on priority queue, where we'll see implementation of priority queues. So this priority queues we are going to implement using circular array or circular movement or circular queues. Okay. So that means the front and rear will move by using this formula f equal to r equal to r plus 1 mod size, right, and f equal to f plus 1 mod size. So this is the circular movement. These are used to for circular movement. So the priority queue implemented using a circular queue. In this priority queue, all the operations, that means full, empty, initialize, then a dequeue, they are all same, right? The operations I'll write here operations like initialize, then empty, right? If r equal to -1 or f equal to -1, the queue is empty. Initialize, f equal to r equal to -1. Third operation is full. Again, the full condition is also same. What is full condition? If r plus 1 mod size equal to front, f, front means f. If this condition is true, that means the location next to r, if that is equal to f, right? I'm not using pointers here, that's why I'm not writing PROR and PRF, right? So I'm assuming that I have access to these elements of the queue. Of course, if I want to access f and r by using this structure name also, I have to use q dot r and q dot f, but I'm avoiding those complexities. Just I'm saying that whatever location this r will give me the value of r. So r plus 1, that is 3 mod size is 6 here. If that is equal to f, right, then we'll say that queue full. The same condition was there in circular queue for checking if the queue is full or not. Same function or same formula we'll use here, same condition we'll use here. Then dequeue operation is also same, right? What is dequeue operation? Remove an element from location f, right? Dequeue operation. Get an element from location f, data of f. Of course, before calling dequeue, I'm checking that the queue is not empty, then I'm calling dequeue. Then after removing an element, I will check was that the only element removed. If it was, then I'll set if only element, if only, then I'll set f equal to r equal to -1. Else what will I do? I will say f equal to f plus 1 mod size, right? I'll increment f by 1, right? So this is dequeue operation which we have seen in circular queue. All these operations we have in circular queue. Please go through the video on circular queues. It is there in the playlist. And the structure also. In fact, this structure, this queue object or abstract data type is same. Struct queue int data of size. Size is a macro, right? Hash define size 6 here. Size of this queue is 6. And then I have int f comma r. Same structure, and this structure we have been using the same structure for all the queues which you have seen so far. Same structure we are using, right? Queue implementation using arrays, whether it's linear queue, circular queue, or doubly ended queue, same structure we are using, right? And these all operations are exactly same to the operations which we saw for circular queue. Only the change is in insert operation or NQ operation. NQ operation, there is a change. We'll see what is that change, right? So let's say this is our queue. 0, 1, 2, 3, 4, and 5. This is data array. This is F, and this is R. As we know that this is a priority queue, the elements with highest priority will be standing at the front, right? F will be pointing, or F will be storing the location of the or the index of the element with highest priority. So let's say So far the queue is like this, and the priority here is the face value of the elements. The priority here is the face value of the numbers. So for example, 30 is having higher priority than 20 because 30 is greater than 20, and 20 is having higher priority than 10. So this is the queue so far arranged according to their priorities. So F in this case is 0 and R in this case is 2. You see, the element with the higher priority is at at the front end, right? So of course, when I perform DQ or when I serve the elements, the 30, which is the element with higher priority or highest priority, will get served or will get removed from the queue, right? So DQ is normal. It's a normal DQ. Remove an element from the front end and increment front in the circular fashion by using F equal to F plus 1 mod size formula. Now NQ is slightly difficult. Why it is slightly difficult? Let us say I want to NQ 40 in this. So what is the NQ procedure? What will I see? What will I do? I'll get the element or the location or the value of R. I'll get the value of R. Let's say I is equal to, let's say I have a pointer pointing here, or I can use the name of this structure q dot R, I'll say, right? Or I have pointer p arrow R. Okay, so I have taken I am using this variable I. So before that variable, let me say that this element to be enqueued is stored in a variable x equal to 40. So the idea is I want to enqueue this 40 in the queue. Of course, we do enqueue from the rear end, right? Now what will I do? I will compare this. See this 40. If it the 40 should come before the elements with less priority. So how will I do that? I will compare this 40 with the element on rear location. I will find what is value of rear. Value of rear is 2. That means the element is there on location number 2. That's the most recent element in the queue. So 40, if had it been a normal queue, I would have inserted this 40 here by saying R equal to R plus 1 mod size. Normal insertion would have been R equal to R plus 1 mod size and P arrow R equal to X. I would have said that, right? So normal insertion, I'm showing you this is normal NQ operation. Normal NQ is R equal to P arrow R, you can say P arrow R, because let's say we have this P pointer pointing, P arrow R equal to P arrow R plus 1 mod size. So this R will be incremented in circular fashion, so R becomes 3, and then I would have said P arrow data. I will go to data array on R location equal to X. That's the normal NQ operation, right? But in case of in priority queues, I will not insert this 40 here immediately by incrementing R, but I will compare this element with the element already present on rear position. If the rear element has less priority than the new element, so I'll take different color. So this is the element on rear position. I'll compare this with the element. How I am coming to this is the element on rear position? By looking at the value of R. R is 2. I'll go to data array in 2 location, right? So data of 2. I'll compare data of 2 because rear is 2. So data of 2 equal to 10. So 10 is compared with 40. So 10 is less than 40. That means 40 should be served before 10. So on which elements are getting served? Which are here on this side. That is the front side, right? That means 40 should be inserted before 10, right? So there is no space here. So I should shift 10 rights, right? That is, I should shift 10 here, right? Then immediately I'll not insert 40 here. And those who know insertion sort, it's kind of inserting an element, insertion sort operation, which we perform this kind of operation in insertion sort. So 40 we don't immediately insert here. We compare 40 with this 20. Again 40 is greater than 20. That means 40 should be served before 20. So 20 should be shifted to right. That is here. So 20 will come here. Then again 40 will not be inserted here because we have an element here. So we'll compare this 40 with 30. 40 is greater than 30. That means 40 should be before 30. So I'll insert 40, insert or shift 30 to this side, and then I will insert 40 here. insert 40 here, right? So that is how I insert, that is how I insert in priority queue. This is the insert operation in priority queue, right? Now how will I write the code for this, right? What will I do? I'll get the location r, value of r in I, right? I will not change I, right? Now after inserting I'll change I, r, I'm sorry, after inserting this 40 I'll change r, because r is no more this, rear is this, right? Rear is 3 location 3, so I'll change this, right, after inserting 40. So now what I did here, if you saw, I saw what is r. R was 2. R was 2. I noted the value of r in I. I use a variable I, right? I use a variable I. Then what I do, I am shifting these elements, right? As long as these elements are smaller than new element. I am shifting these elements on this side as long as these elements are smaller than x, or as long as x is greater than these elements, I am shifting these elements towards right, right? That means I am saying that data of or p arrow data, rather I'll say p arrow data of I plus 1, right? Because if I is 2, the new this is getting this element which was on I location is going to location I plus 1, right? So p arrow data of I plus 1, right, is equal to p arrow data of I, right? If I consider, or I store the value of r in I, right? I store the value of r in I, so I will be 2, I will be 2 in the, right? I will be 2. Okay, let me take another queue here, because slightly messed up the, let me take another example here. So this is the queue, this is array queue, 0 1 2 3 4 and let's say 5, then f r. So this is 30 20 and 10. F was 0, r was 2, f was 0, r was 2, right? And then we wanted to insert 40, x is equal to 40. What I am doing, I am noting the value of I, r, I am noting the value of r in a variable called as I, right? Because I want to use I to traverse in this direction, right? I will initialize I to r, right? So this I will be initialized to r. R means location r, or value of r is 2, that means location 2. This I will be initialized, this I will be initialized to location 2, because r is 2, that is where the last element is present, right? So I will be initialized to r. Then I am comparing data of I with x. I am comparing data of I with x, right? So if data of I, that is data of 2 in this case, is less than x, or if x is greater than data of I, what I am doing, I am shifting this the data of I to data of I plus 1, right? So data of I plus 1 is equal to data of I, right? So in this case, if I show you, I is 2 because r is 2, right? And what is data of I? I is 2. So data of 2 is 10. Data array of 2 is this. 10 is 10 less than x. X is 40. Yes, 10 is less than 40. So I should shift this 10 by saying, what is this location? Data of I plus 1. Data of I plus 1. I is 2. So 2 plus 1 is 3. 2 plus 1 is 3. Data of 3. This is data of 3 is equal to data of 2. So this 10 comes here, right? Then again I do the same thing, right? Now I'll decrement I. Before that, I'll decrement the I by saying I equal to I minus 1, because I am going in this direction. I was 2, now I will become 1. I will become 1. I will become 1. So I is getting decremented. I is getting decremented, right? So I is getting decremented. So I will decrement I. Then again I'll compare if same loop, same if I'll write here, same if I'll write here after decrementing I, and now I is 1, so data of 1 is compared with x, so data of 1 is 20 and that is less than 40. So again I shift data of I plus 1 is equal to data of I is 1, so I plus 1 is 2, so data of 2 is equal to data of 1, so 20 will be shifted here. Again I'll decrement I will come on 0 location, right? So when I comes on 0 location, again after this loop, after this if, I will say I equal to I minus 1, and I'll write the same if here, comparing data of I, that is data of 0 with 40. So again 30 is less than 40, I'll say the same thing, data of I plus 1 is equal to data of I, that is I plus 1 is I 0 plus 1 is 1, data of 1 is equal to data of 0, so 30 will be shifted here. Then now in case if I have to decrement this I again, this I should be decremented in the circular fashion, or it should be moved in the circular fashion. So I is getting this kind of movement, right? Remember DQ, doubly ended Q. In doubly ended Q, we have given this movement to front when we were inserting from front end. So right, front was going in this direction, right? Inserting from front end. Similarly here, this I is going in this direction, it is decrementing, right? So that's why I is getting this movement, and whereas F and R are going in this direction, F and R are going in this direction, right? And when F and R come to the last location, this will get this movement, this kind of movement, right? F and R will get this kind of movement. So let me take another color here. So this is not F, this is I's increment. I is getting decremented like this, and when I comes to the 0 location, if you decrement it one more time, it will come to the last location by this kind of circular movement. And for F and R will be growing in this direction, that means growing in this direction once F and R come to the last location, and if we increment one more time, this kind of movement for F and R, right? So this kind of movement we have seen in doubly ended Q, right? So doubly ended Q. So I is incremented. If I write the formula for I, or decrementing I, it is like I minus 1, in fact, because we are decrementing I minus 1, right, plus size, right, mod size, right? So this formula is useful, this mod size is useful especially when you come to the last location, right? So right, when you come to the last location, right? So till this point, the decrement is a linear decrement, which can be done by using this, or this is a linear decrement till you come here. But when you come on this location, if you want to go like this complete formula will be used. I minus 1 plus size, percent size, decrementing I, and then data of I will be compared with X, right? Whereas F and R are incremented in the normal fashion, F equal to F plus 1 mod size, and R equal to R plus 1 mod size, right? So we insert 40 here because we don't want to, because this was the last element in the queue, there is no more element after this. So 40 will be inserted here, right? But this you will go on doing as long as you have an element on the next location, right? Okay, so this is what NQ operation in the priority queue, right? So slightly involved operation. Let us write an algorithm for this, right? I'll write an algorithm here. This is our queue. I'll quickly draw it. This is queue, data array, five, and F, and this is R, right? So in our case, this was 30, 20, 10, R was 2, F was 0. Okay, and let's say we have this pointer P, because I am calling the function NQ, right? NQ or insert, this is 10, right? by after making sure that the queue is not empty, queue is not full, I am calling the function enqueue, right? My call to enqueue is enqueue and queue. I am passing the address of this queue and the element x, right? So my enqueue function will be, here is my enqueue function, void enqueue, enqueue, and to this we are passing address of this queue, so I need a structure queue type pointer, struct queue, right? And then struct queue star p, and then we are passing one integer element, so int y, right? So again, before doing enqueue, two situations if the queue is empty. The first situation is queue is empty. How will I come to know queue is empty? If p arrow r equal to -1, queue is empty. In that case, we'll set both f p arrow f rather p arrow f, because we have a pointer p pointing this queue, p arrow f equal to 0 and p arrow r equal to 0, and then we'll insert in the data array p arrow data on rear location, p arrow rear, which is 0 in this particular case, is equal to y. So this will do when the queue is empty, right? Else means queue is not empty, else queue is not empty. In that case, what will we do? As I said, this x which is there in y here, let's say we pass 40, y is 40 and this x here was 40. I pass this x by value, so this x is copied in y. Now what I am doing now, I am retrieving the value of r, which is the location of the last element in this array, right? So I am saying else I is equal to p arrow rear, right? So what is rear here? Rear is 2, so I will be 2. In this particular case, I will be 2 because rear is 2. Then I am going to compare this 40. In fact, this y I am comparing, y and x are same, but x is known in main, y is known in enqueue function. So I am comparing this, let me take black color. So I am comparing this 40 with the element present on the last location or ith location. I have initialized I here. I have initialized this I here, right? So I'll compare, right, data of I with x, with y in fact, right? Because I am here in enqueue. Enqueue knows y, enqueue do not know x, because x is local to min, y is local to enqueue. So I'll compare this data of I with y. If y is greater than data of I, I'll shift data of I to data of I plus 1, right? That is this location, I'll be shifting this element, I'll be shifting here. When this is smaller than 40, right? So I'll be doing that, and then I will decrement my I in this direction, by using the formula which we saw earlier. What formula? This formula I'll use to decrement I. And once I comes on this location, again I'll be comparing this data of I with x. If x or y, if this y is greater than data of I, will be shifted to I plus 1, data of I plus 1. I was 1, I plus 1 is 2, so 20 will be shifted to data of 2, this location, right? And then again I'll decrement I will come on 0, and data of 0, that is 30, is compared with 40. Again 30 is less than 40, so shift 30 also, right? Shift 30 also, and then insert this shift this 30 here. Then if we have a number here, then again decrement I and check whether the number of this location is greater than y or less than y. So you go on doing this shifting as long as the element on that location is less than this element, right? Because this priority is higher than these elements, right? So that's why I'll be using while here, while y, that is this element, is greater than p arrow data of I, data of y. while this y is greater, compare this y with this element, compare this y with this element. This is ith element, I is initialized here, right? If y is greater than this, then shift this, right? Again, as we are in while, decrement y and compare this element with decrement this I and compare this element with this. So again, if this is less, then shift, right? That's why we are putting this in while, right? We wrote so many ifs here, no? Here, these ifs, rather than writing those ifs, I am using a loop here, right? And this loop is, the shifting will be done, this shifting will be done as long as the element here is having less priority than y, right? This shifting will be done as long as the elements here have less priority than this y. So what I'm doing, I'm doing shifting, right? What shifting I'm doing? Data of I plus 1 is equal to data of I. So p arrow data of I plus 1, right? Of course, this I plus 1 should also be in circular fashion, because we are going in this direction, right? I plus 1 is in this direction. That's why I plus 1 mod, I plus 1 mod size, right? I is incremented in the circular fashion, right? Why this is so? Because when you are on the last location, right, when you increment your I should go to this 0, right? I should go to this 0. That's why this increment is in the circular fashion, right, in the right side, right? I am decrementing I for comparing the elements on these locations with y, right? But insertion is happening on the I plus 1 location, right? So you see here in this example, I'll show you here. I is 2 because r is 2. So what I did, I compared y is y greater than data p arrow data of 2. So y is 40, is 40 greater than p arrow data of 2. What is data of 2? Data of 2 is 10, right? Is 40 greater than 10? Yes, answer is yes. In that case, what will we do? P arrow data of I plus 1, next location to I plus 1. I is here, right? Next location is this one, right? Next location is this one. But mind well, now this is okay if I do I plus 1, data of I plus 1, this is okay in this particular aspect. But imagine if I is here, if our I is here, in that case, what is the next location? Next location is 0. Next location is 0, no, because we are using circular queue. That's why this formula I should use for next location, right? Next location, p arrow data of I plus 1 is equal to p arrow data of I, p arrow data of I. So this is slightly tricky, right? And then how will I decrement I? Now I am decrementing I. So p I is equal to I minus 1 plus size mod size, because we are decrementing in this direction. So circular decrement by using this formula, right? And then let me continue here. Okay, so what we did, we did the comparison, right? And if y is greater than this, we shifted data of I to data of I plus 1, right? I plus 1 in the circular direction. Again, I'm repeating, this will come in effect when our I is here. When your I is here, I plus 1 should be in this case a 0th location, that is this one. For this, I am giving circular increment to I also, right? To find the next location. Next location of I is found by using circular formula, because we are using circular queue, right? Normal simply data of I plus 1 will not work, because we are, the next location for 5 is 0. Next location 5 is 0, right? Then I'll decrement I. After decrementing I, so this is how I'll decrement I. Now after that, I'll check if from here So here I'll come, if I plus 1 percent max, max means size, I'll take here size, is equal to P arrow F, right, P arrow F, then I'll break this. That means when to stop this, right, right, as long as this condition is true, right, as long as this condition is true, we'll go on shifting. But at some point in time, we'll reach to a location where I will be equal to F, right. We are incrementing I, no, we are incrementing I in this direction, right. So that means the next location, wherever I is, right, wherever I is, if the next location is front, right. So if I plus 1 mod size equal to P arrow F, then we'll break, right? Right, that's it. So what we did here, this is purely for shifting, right. And then when we'll stop this loop, we'll come out of this loop in two cases. When the element on ith position in the data array is greater than y, right. The first condition is the element on ith position. Imagine here I have 60, so I will stop this shifting, this loop will break as soon as our I comes to 0. This loop will break, right. So this is the first situation when the element is greater, higher priority than this element. The second situation is wherever our I is, let's say I is here, and the next location to I is front, that is I plus 1 mod size is equal to front, right. And that is the situation, because that location is not empty, next location is not empty, this is kind of queue full, because I am checking the next location. No, I want to shift this here, let's say I want to shift this here, right. But this location is already occupied. When this location will be occupied? When front is here, right. When the next location, I want to do this shifting, right. I want to shift this 10 here, right. So how will I do that? Data of I plus 1 is equal to data of I. But if that location is already occupied, that location is already full, when will I come to know this is full? When front is there, right. When front is there. So that's why I plus 1 mod size is equal to P arrow front. So that time also I'll break, right. So this is how, so this bracket closes with this, and for this we have this bracket, right. So this is NQ operation in circular queue. So we have seen all the operations, not circular queue, priority queue, NQ operations in priority queue. So this loop will be used to shift the elements from data of I to data of I plus 1, right, as long as the priority of ith element is less than the priority of y. So shift decrement I, what is I am doing? Shift decrement I, shift I data I to data I plus 1 and decrement I, and repeat this, that's why this while, right. So when we'll stop, you will stop in two cases. First is the element on that location, ith location is greater, like this, is greater than this element. That is the first case when we'll stop. The second case is we have the ith next location to I is full. That means I cannot do shifting. When I cannot do shifting? When the next location here is occupied. And when it will be occupied? When front is pointing there, that time this location is occupied. So this is the second condition, right. So first condition, when we'll break this file, when we'll stop shifting. The second condition we'll stop shifting is the next location to I is, see, next location for shifting we are checking in this direction, that's why I plus 1 mod size. Next location for shifting we are checking in this direction, right. Checking means next location for inserting is in this direction, that's why we are doing I plus 1, right. and next location to compare is in this direction, right? Okay, because we want to shift from these elements like this, right, that side. That's why I is decremented, right, and it is the value on ith location is shifted to I plus 1 in the circular fashion. So I hope you understood this. I tried my best to explain this, but still, if you have doubts, you can go over this video again. I'm sure you will understand this, right? So probably we'll see one more example numerical on priority queue, especially NQ operation in in one of the video. So stay tuned and see you there. Thank you.